Equilibrium of force and space. Vector analysis is very useful in determining the magnitude of force or the value of forces and the structural members. So this is useful in the truss analysis in 2-dimension or in 3D dimension, especially when the arrangement of the members are very complex. So here, the vector quantities are characterized by the point of application, magnitude, and direction. So from point A to the terminal point here, so this is the vector. It has the direction and it has the magnitude. It can be resolved into components in any direction you want it to be, but having the same effect on the particle. So it can also be resolved into rectangular component if fx and fy are perpendicular to each other. So by introducing the unit vector I and j along x and y axis respectively. So this is the representation of the horizontal component and the vertical component. This is equivalent to scalar component multiplied by the unit vector along x and y axis by I and j. So by trigonometry, you can analyze that the horizontal component is the magnitude of the vector multiplied by cosine theta and fy by the sine theta, and we can solve for the angle theta through trigonometry. So the same with the 3-dimensional direction. So be careful of the orientation of the axis. Sometimes the z-axis represent the vertical axis. So here, this is the y-axis is in the vertical and x-axis along the horizontal, and the z-axis is the axis towards us. The vector unit and the 3D dimension is I, j, and k. So this stands for x, this is for y, and z direction. And the component is here. fxi, fyj, fzk. If you use the angle, so this is cosine I, cosine theta j, cosine theta k. So the value of main vector is the product of the magnitude and the unit vector. So this one is the vector. So if that is the force F, that is the square root of the fx square plus fy square plus fz square. So the unit vector here is equivalent to 1 over d. So this distance is the distance of this vector, and that distance will be equivalent to square root of the projection of its length to the x, y, and z direction, x squared plus y squared plus z squared. Okay, let's apply the theory to the analysis of the space trusses. So here is the example, the transmission tower held by three guy wires attached to pen A. So that's pen A anchored at B, C, and D. So wire AC has the magnitude of 3.68 kilonewton. Determine the force P exerted by the tower on the pen at A. Okay, so to maintain the equilibrium and the tower stands in its straight direction, so uh, the wires have the tension effect on the tower. This is wire AC, and AD has the tension effect, also the wire AB. So that is AB, AC. So to remain equilibrium, the tower exert also the opposite force. Let's say this is force P exerted by the tower. So through analyzing the joint A, we have the summation of force vertical, force horizontal, and force along z-axis. So this is the orientation of our axis. This is the y direction going up, positive. This is the x direction going to the left, positive, and z direction towards us, positive. And the opposing direction will be negative respectively. So get the length of wires AB, AC, and AD. So the length of the wire AB is 21 here, because we have the from point A, so we have 9 going to the left, and Z from A towards us 6, and Y 18. So 9 plus 18 squared plus 6 squared, that is 21, and for AC 23, and for AD 22. Okay, so for explanation purposes, I tabulate the vector AB, vector AC, AD, and P. So for vector AC, we have the magnitude, and the magnitude of AB, we stand it for slant AB, AD, and vector P. So 3.68 for vector AC. So this is the unit vector along x-axis and along y-axis, this column, and this column z-axis. So this is negative 9/21 because the x is going to the left for AB, and for z-axis from A, this is towards us, the 6 meter. And for y-axis from point A to point O, that is the plane of z and x, that is 18. So going down, force is negative, so that is negative 18/21. And for AC, that is positive 6/23. And for y, negative 18/23. And for z-axis, this is towards us, 13/23, that is positive. For AD, 4 going to the right, the x-axis, that is positive. And for y-axis, so going down, force component of y-axis, negative 18. And for z-axis, negative 12. This is 12, negative 12. Okay, so from the definition, the vector F is equivalent to its magnitude multiply V, the unit vector. So here, for summation along x-axis, for AB along x-axis, so I rearrange it for the horizontal to be as row. So negative 9 over 21 multiplied by AB. That is the supposedly the magnitude that is going to be determined later. So and when I entered it in the calculator, I get the answer for AB 4.96 kilonewton, for AD 6.41, and for P 12.40 kilonewton. And the required answer for the force P that exerted by the tower is 12.40 kilonewton tension, and that is the answer. So let's go back to this arrangement. So for so it's negative, so the value of AC, because it has already the magnitude at 3.68, so later we can find out that the AB is 496 and AD is 6.41. So when you enter it in the calculator, so this is the constant. It's like the three simultaneous equation having three unknowns, that x, y, and z equals constant, and this one is the coefficient of the variable. Okay, so in the simultaneous equation, our variable is AB, AD, and P. So the coefficient along x is negative 9 over 21, for AD 4 over 22, and for OP, so 0. So I represented 0 because the P is acting just along the y-axis. So this is going up, so along y-axis, that is 18 over 18, because the 18 is the length of the tower. So 18 over 18, that is 1. So along x-axis, that is have no 0 magnitude of P. So along y-axis, that is 1. This is 1. Along z-axis, there is no 0P, so that is 0. So this is the projection along along y-axis for AD, and for AB negative 18 over 21, and along z-axis for AB, AD, and P is 6 over 21, 12 over 22. Then here, this is the C is positive 623, for Y negative 1823. When you transpose it to the equation, let's say this is our left equation equals right equation. So primarily, the left plus right equals 0. So when you transpose the R to other side, it will become negative. So I already changed the sign, so that when you enter it into calculator, this is easy. Okay, so in your scientific calculator, you can see this format. So you find press alpha, and then the mode, and then you can find the display. So just select equation 5, and then from when you press the equation 5, you can proceed to 2, having three unknown x, y, z equals constant. So this is the display, and you enter all the data that we gathered. So by filling up the data into the calculator, so you can proceed to press the equals for x, y, and z. The x represent for AB, and z represent for AD, and z represent for P. So depend on how you arrange your variables. So this is the answer for P, the answer for D, and answer for AB from the calculator. Okay, so another problem, the J cables and this arrangement. So this is the orientation of our axis. So this is the Z axis towards me, positive, Y axis going up, positive, and this is okay, X axis. So point A is 240 millimeter above the reference line from zero axis, 0 point or datum. Point D is 960 from the reference, and point B and point C is in the 0 level. So for member AB, so from point A, the question here is what is the value of P when Q is equals 0? What is the value of P? So the force acting on P is tension. So for equilibrium, so let's assume this wire AD as tension, wire AC also tension, and wire AB is tension. So wire AB, so I get already the total distance or length of AB, that is 1060 millimeter, for AC 1040 millimeter, and for AD 1220 millimeter. So I will get the unit vector. So for AB, so along x-axis, that is going to the left, negative 960 over 1060. So I put it here, negative. So along y-axis, so from point A to the level of point B, so you have to go down. So this is negative 240. So that is negative. This is negative 240. Here, I put it here, negative 240 over 1060. And then from point O to point B, because point A is in line with point O, from point O to point B, that is 380. So going towards me, that is positive 380 over 1060. And for AC, so you'll do the same. So X towards away from me, that is negative. Okay, that is for Z axis. From point O to C, that is away from me, that is negative 320. So that is negative 320. And for x-axis, that is from point A to point C, projection of x, that's negative 960 over 1040. And for y, we have the same, you have to go down, so this is negative 240. And for AD, which has already the magnitude of 305, so this is the magnitude, I put it here. So negative 960 again, going to the left for x. And for Z axis, so this is away from me 220, so this is the negative 220 over the total length of 1220. And this is 960 from point O to D. Vertical projection 960 minus 240, it will give you 720 positive, because this is going up, force vertical over 1220. So I rearrange it in the horizontal manner. The column become the rows. So I enter it into the calculator and proceed. So the constant is the magnitude of AD. So this is for x, along x, that is 960. So when we transpose 8 to the other side, it will become positive 960 over 1220 multiplied by 305, and I get respectively. So I get from the calculator the value of AB 447 kilonewton tension, AD is 342 tension, and P is 960 kilonewton tension. Okay, so let us apply it into the analysis of truss analysis. So here is the truss. So determine the force in member CD. So in the problem, but I done it here. I solve all the magnitude, all the stresses of all the members. So I started it with joint C. So we have the going down force of 2 kilonewton here. So I will assume the force CD as tension. So force CD, tension also, and this is, I will assume it CB as compression. Okay, so this is a equilateral triangle. So the overall length of CD is already 2. This is 2 and this is 2. The length of member AB and member CF is 3 meter. So the diagonal that having the projection along X, Y, and Z axis. So you get the same procedure we discussed lately. Okay, for the triangle, so this is 2 for member AD. This is 1, so this will become square root of 3. Okay, AD. Okay, for member CD, along X direction. Okay, sorry, I have the wrong entry. This is not square root. This is just 1 over 2. And this is 1 over 2. Okay, the orientation of our axis, the Z axis become the vertical. So this is Z, this is Y, and this is the X axis. Okay, for X axis, so we have the half. This is 1 over total length. This is 2. So for Y axis, it has no projection. That is why this is 0. And for Z axis, that is the vertical. If this is going up, this is positive, which is the vertical length or component of CD is square root of 3 over 2. So this is positive. So going this is positive 1 over 2 because the x-axis is towards me for CD. So for CB, this is CB. So it has the projection along x-axis only. So negative 1 because I assume it as compression member. So negative 1 because 2 over 2 is 1, so negative 1. So it has a projection at y, no projection along y, no projection along z. That's 0, 0. So for CF, so it has projection only for y-axis, y-axis. So the y is opposing towards to the left, so we get the negative 1. And for constant, we have the 2 kilonewton. It has the projection along z-axis, negative 2. Negative 2. Okay, so you rearrange it into horizontal arrangement and input it into your calculator. You can get the value of member CD, 2.309 kilonewton tension and 1.155 kilonewton compression. So the calculator also will give you the negative if it is giving you the negative sign, so the assumption is the opposite and you can correct it already. So for member, proceed to the another joint. So for joint D, so the CD is tension, so I put it here, tension. So it has the magnitude of 2.309. Ayan. 2.309 tension. So I assume it at tension. So I will assume it also tension. The member DF and member DE also as tension. So you can find it in my tabulation. So the direction. So according to your direction, you must get the sign. So for DE, so along for DE, it has the projection along y-axis only. So that's negative 1 because I assume it as tension going to direction going to the left. So negative 1. So x 0, 0 because it has no projection there. So for member DF, so it has the x, y, and z direction. So from point D to point F, which is in the level ground level. So negative 1 for x. So okay, this is 1, this is 3, square root of 3, this is 2. So negative 1 because it's going away. Away from me. So this negative 1 over square root of 13 because the length DF is equals, that is 3 square plus 1 square plus 3. This is square root of 3 square. That will give you square root of 13. So along y-axis, DF, so this is along y-axis, so this is the 3. That's why this is negative 3 over square root of 13. And for z-axis, that is the vertical component, this is square root of 3, negative over total length. And for dB, so this is dB. So if this is going up, okay, the y direction is positive, square root of 3 over 2. It has 0, no direction or no component, and y direction, and the x-axis is negative 1 over 2. Then CD, which has what we computed in the preceding joint. So we have 2.309. So multiply it, then transpose it to the other side, and the calculator will give you the answer. So DE for tension, so this member is 0 member, and DF is 4.16 compression. Then having the stress, compression or tension, you can proceed to joint B. So joint B has the, so when you represent the joint B, so this is the 2 kilonewton. So this is AB. This is BF, and we have BE. So we have the diagonal member on the plane of XA, that is member BF. So you have the 3 unknown. So be careful of the sign and direction of the component. So this is the answer. BF 3.46. So it is not tension, but this is compression, and BF is tension and BE is tension. Then for joint A, I get the member AE, AF is 0, and this is RF having the 4.49 magnitude, and for the rest joint F, FA. So I sum up all the stresses and the table. That's all.